Let us consider a cube of length L. Let this cube be heated to a temperature T. After heating, the length of the cube will increase. Let delta L be equal to increase in length, and L the original length of the cube, original length of the cube. Then we defined a factor called alpha, which is called the coefficient of linear expansion or linear expansivity, which is defined as the change in length by original length per unit rise in temperature, where delta T is the change in temperature. Change in temperature. So this quantity is called, this quantity change in temperature, this factor is called alpha. Let's call that as equation number 1. Also, the length here also increases. Suppose if you take this area, it will be a square of length L. So after heating, here there is an increase in delta L. Here also there is an increase in delta L, which means the new square will be like this, which means there is an increase in area of the square. And we defined another factor called beta, and beta is called the coefficient of superficial expansion. We define that as change in area by original area per unit rise in temperature. This is called beta. Let's call that as equation number 2. So how will you find a relationship between alpha and beta? Let's write what alpha and beta is. Alpha means coefficient of linear expansion, and beta is again the coefficient of superficial expansion. So that's our alpha and beta. So let's calculate the beta. We have beta is equal to, we have change in area, we have the original final area, let's call that AF, will be L plus delta L whole square, because the length of the new square is L plus delta L, and the initial area is L square, because initial area is this much. So change in area means L plus delta L whole square minus L square divided by original area is L square times delta T. So if you simplify this, you will get beta is equal to, expanding this, it will be L square plus 2L delta L plus delta L square minus, so the expansion of L plus delta L square is this one, minus L square divided by L square delta T. So you can cancel this L square and this L square. Delta L is already very small, so delta L square you can neglect. Delta L square is approximately 0. So the value is 2L delta L divided by L square delta T. You can cancel 1L and 1L in the denominator. So the equation will be beta is equal to 2 delta L divided by L delta T. So that's our beta. So if you compare with that of equation number 1, this term is alpha. which implies beta is equal to 2 times alpha, or the coefficient of superficial expansion is 2 times the coefficient of linear expansion. Again, if you consider, let's erase this. We have alpha equal to change in length divided by original length per unit rise in temperature. That's the equation one. So there is another factor called gamma. Gamma is called the coefficient of cubical expansion. Let's write it here. Gamma is equal to coefficient of cubical expansion, which means change in volume by original volume per unit rise in temperature. That is the value of coefficient of cubical expansion. So change in volume, we have the final length of the cube is L plus delta L. So the initial volume, let's write it in here. We have initial volume of the cube Vi, let's represent that as Vi, is equal to L cube. And the final volume is equal to, final length is L plus delta L whole cube. So change in volume is equal to L plus delta L whole cube minus L cube divided by original volume is L cube delta T. So gamma is equal to, on expanding this you will get L cube plus 3L square delta L plus 3L delta L square plus delta L cube minus L cube divided by L cube delta T. You can cancel this L cube and this L cube. This thing is 0 because L is already small, so delta L cube is 0. Similarly, this one is also 0. Since delta L, that is delta L square approximately equal to 0 and delta L cube is approximately equal to 0. Since delta L is very small. So gamma will be 3L square delta L divided by L cube delta T. You can cancel this one and this one. So final equation of gamma will be gamma is equal to 3 delta L by L delta T. So this one is again, if you compare this with equation number 1, that is alpha. So this is equal to 3 alpha. So gamma equal to 3 alpha, which means coefficient of cubical expansion is 3 times coefficient of linear expansion. So that's the relationship between alpha, beta and gamma. So what is the ratio of alpha is to beta is to gamma? We can write that also. That is, let's write alpha is to beta is to gamma. We already found that alpha, let's write alpha as alpha, beta is 2 alpha and gamma is equal to 3 alpha. Cancel this alpha, every alpha, so the ratio is 1 is to 2 is to 3. Clear?